All right, welcome everyone to the second part for the differentiation topic. We're going to continue our road on making sure that you know all the concepts in the differentiation exam. If you haven't watched the first video, make sure you watch that one first because we go through all the fundamentals on all the rules in differentiation. The link will be down in the first part in the description. So let's get started. Our second topic is all about using derivatives. What can we use it for? How are we going to use it? And we will also do some more strategies on how to solve more complicated functions. So the first part that we need to know is we need to learn about the tangent line. So the tangent line will actually be a line that looks very much like our real line, like our original equation, but only at a specific point. So if we zoom in as much as we want at that point of intersection, then it will look that our straight line will actually be the same as the curve that we've got. Now, this does not happen if we're further away from the point. Now, when we look at the tangent line, we have a couple of properties that you need to know. One is that the gradient of the tangent line is always equal to the gradient of the function at the point of intersection. Also, the tangent line is supposed to be a linear approximation of our curve. So at the point where we're interested in at x0, we have our curve, but it looks like a straight line. So we're going to have to use a straight line formula to figure out the equation of a tangent line. Now, to find this straight line formula, you should know y is equal to mx plus b is the form that we want to have our final answer in. That gives us the gradient and the y-intercept for the straight line, so the tangent. Now, in order to find this, we need two things. We need m and we need our y-intercept b. Well, in other words, we actually just want the gradient and a coordinate point where their intersection is. Because then we can use a new formula that you've been introduced to this year. Y minus y naught is equal to m times x minus x naught in order to get straight to this form if we're expanding. So from this slide, just remember we need the gradient and we need a point, more precisely the point of intersection. So let's have a look at our example. We have our function y is equal to x squared, and we are looking at the tangent line when x is 1. So remember, we need the gradient. So do we get the gradient from the derivative of our function? Because at that point, the derivative of our function, the gradient of our function, is the same as the gradient of the tangent line. So we find dy by dx, which is 2x, and we now substitute n1 into this equation to find the gradient of our original function and the tangent line at the point x is 1. We get the slope of 2. Now we also need the coordinates of the point, and it's been given here 0.11, but how do we find the y value for this point? We know x is 1, but how do we find y? Well, always remember the original equation y is equal to x squared gives us the relationship between x and y. So we can substitute in 1 into x squared. 1 squared is 1 to get the y value of 1. Now we just use the formula that we've just seen. Y minus y1, m times x minus x1. And now we substitute our values in, our point x0 and y0, and our equation gradient of 2. We can expand our equation to get the standard form, which you should leave as your final answer for the equation for the tangent line. Now, here's another example. We have our function as sine of x, and we want the tangent line at pi over 2. So again, we're given a function sine of x. We need the derivative to find the gradient. So the derivative is cosine of x, And we now need to evaluate, so substitute in pi over 2. Now we get that the slope is 0. And again, think about how we got the y value here for a point. We substituted in pi over 2 into our original equation sine of x. Once we have a point and the gradient, we can use our function, just like I've shown you, y minus y naught and so on. Substitute in your values, expand the brackets and solve for y, and you get y is 1. Now, when we talk about the tangent line, we also need to talk about the normal. The normal is also a straight line, but it is perpendicular to the tangent line. That means we're on a right angle. We have a 90-degree angle between the tangent line and the normal line. So if you're asked to work out anything with the normal, the procedures are exactly the same, with one different step. The gradient of the normal is not the same as the tangent line, but we still need to figure out the gradient of the tangent line in order to find the gradient of the normal. I've given you a formula, and what this means is we're just going to make our gradient from the tangent line negative and put it in the denominator. With other words, this is the reciprocal. Well, the negative version of the reciprocal. So, if your gradient of the tangent is 2, then the gradient for the normal is negative 1 over 2. But if your gradient for the tangent is a fraction, let's say 1 over 3, then the 1 over part flips the fraction around. So if your tangent line has gradient 1 over 3, then the normal has gradient negative 3 over 1, which is negative 3. So we just want to make the gradient negative and flip the fraction around. Well, here's an example. It should work the same way that we've just worked it out. So we start again with x squared. We've seen this example before. We found our slope was 2, but our slope for the normal is exactly the reciprocal negated, so 2 becomes negative 1 over 2. Well, the coordinates actually remain the same because they're going through the same point, which is the point of intersection between the curve and the tangent, and of course the normal. Well, at the bottom I've substituted both the equation for tangent and the normal line and solved, so make sure that you're familiar with this step. This question will come basically in every exam. There might even be multiple questions that require you to calculate anything regarding the normal or the tangent line. Questions might ask you, find the gradient of the tangent at x is 4. Well, you know how to do this if you know this whole process. The question might ask you for the gradient of the normal when x is 4. Well, you know how to do it the same way, but you don't need to complete and finish with the equation. You could be asked for the equation of the normal and the tangent, and you could be asked to continue working from there using the normal and the tangent line. Now here you can see a few examples. Hopefully you have attempted these. Make sure you're pausing the video to go through some of those examples. I highly recommend that you know how to form both the normal and the tangent equation without any problems. So here's just some more examples for the normal. It's the same equations, but finding the equation of the normal instead of the tangent line. Now, parametric equations can be identified very easily and are usually considered a higher or harder question, higher mark question. So when we're looking at all the functions that I've given you, I have been given you y is equal to and then some function of x. Or I gave you f of x is a function of x, which is the same thing. However, parametric equations, they have a third variable. The x and the y coordinates are actually defined on a third variable, often use t for time. So you can identify parametric equations very easily if you've got an equation for x and an equation of y, both having a different variable, for example t. Now what do we do in this case? We still want to know the gradient, so we still want dy by dx. Well, let's have a look in our next slide where we do some examples, but we need to be able to use the chain rule to put a few expressions or terms together to make our dy by dx. At the bottom, I have just written the standard form of the chain rule that you often use. Now I've marked in yellow in the first part dt by dx, because if you differentiate x with respect to t, and we will see that, you get x dt, not dt dx, so you have to switch them around. If you don't want to do that at all, just stick with the second rule, but you have to learn this one by heart. It is dy dt in the numerator and dx dt in the denominator. So if you're not sure, the first one, otherwise the second one, is a go-to. This will not be on your formula sheet. Let's just do a couple of examples. First of all, how do we recognize that we have to use parametric equation procedures? Well, here we can see x and y are separately defined using their own formula. So here we can just differentiate both of those equations, but now we have to differentiate with respect to t, because that is our variable. So in the first part, we're going to differentiate with respect to t, giving us a dx dt, and then on the other side 2t. So we just differentiate as normal. We just need to make sure that we name this derivative correctly. The same way it goes for the second one. We're going to get a dy with respect to t is equal to differentiating this side, which is 3. And now if you remember, we had dy dt in the numerator, dx dt in the denominator, and we're good. Now here are a couple of examples that I would like you to try. We're actually going to do one of these examples together, just so you can also see me using the other way of constructing our own chain rule. So let's have a look at this part here. I will copy the question for you. So we had been given x is equal to t cubed, and we've been given that y is equal to 2t plus 1. So using parametric equation procedures from this one here, we get dx by dt is equal to, and now we get 3t squared. Whereas on this part, we get dy by dt gives us just 2. So now what we're going to do is, if you remember the formula, it was dy dt divided by dx dt 3t squared, which is going to be our answer. But let's use the created chain rule in case you forgot this rule in the exam, or if you have a more complicated example where you have multiple derivatives. We want to have dy by dx. So we're going to have kind of like fractions. These are not typically fractions, but you can treat them as one for this. We want to have a dy, and we want two things that are going to cancel out. Dy is in the top, and our dx is going to be in the bottom. They have to be on separate fractions. Now, whatever we have in between doesn't matter as long as they are the same in the numerator and the denominator. Now, we don't actually want to cancel them out. We want to use the fact that the combination of these two makes our dy dx. So let's put these in. So we get the derivative dy by dx is going to be dy dt. Well, dy dt was 2. and we multiply this by dt dx. But we don't have dt dx. We only have dx dt. And this is why it's so important to write it the correct way. Now, what we do is we just take this one. We just need to do the reciprocal, so 1 over. So this is going to be 1 over 3t squared. If we put these together, we still get 2 over 3t squared, which is not surprisingly the same answer as if we were doing it the other way. So make sure you give some of these questions and examples a go. Pause the video, make sure you know how to do these, because these will give you a higher mark every time these questions come in an exam. They're not too difficult because the actual questions will have easy steps to differentiate, because they're testing you on, do you know parametric equations, not can you differentiate very difficult equations. So let me give you the answers. Check if these are the answers that you got. You might have to simplify a bit using algebra, but you should be able to get to all of these. Now, usually parametric equations ask you for coordinates when they give you a certain gradient. So again, they're going to give you a gradient, so we need to find dy by dx first. We can then substitute the gradient into dy dx and solve for t. Well, if we do this, we find the value for t where we have a given gradient. How do we now find the coordinates? Well, we have specific equations both for x and y in terms of t. So let's see a couple of examples. Now, the first example is when we have x is t squared plus 3t plus 0 or nothing, and y is 2t. So we've been given to find the points where the gradient is 2 over 3. So let's have a look. Try and pause the video here and see if you can find the derivative dy by dx. We have x is t squared plus 3t and y is equal to 2t. Again, each of these we'll have to differentiate separately. So for the first part, we're going to get dx dt is equal to 2t plus 3, and dy by dt is equal to 2. Using the shortcut, we get dy by dx is dy by dt divided by dx by dt, which gives us this. Now we've been given here that the gradient m is equal to 2 over 3. So what we can do is we can take our gradient and set it equal to our derivative, because the gradient function gives us the gradient. So let's do that and solve. So if we're setting this equal to our gradient, we get equal to 2 over 3. So how do we solve this equation? Well, we have fractions, so we want to multiply by the denominators, cross multiply on both sides. 3 times 2 will give us 6. 2t plus 3 multiplied by 2. Now here we cannot forget brackets because we're multiplying one whole part by 2. So if we now expand this, then we get to 6 is equal to 4t plus 6. Well, this is a very simple equation, so let's squeeze it in here before the page ends. We do minus 6 on both sides, then we have 0 is 4t, divide by 4, then we get to t is 0. Now we've found when we have the gradient of 2 over 3, exactly when t is 0. But don't forget to now go back and use the value for t that we've got to substitute them back into our original equations to actually find the x and y values. So what would be the x and y value here? Well, x would be substituting in 0 for t, which is 0 squared plus 3 times 0 is 0. And for y, 2 times 0, which is 0. So the final answer would be to write down your coordinates 0, 0, which is the coordinates at which we have the gradient 2 over 3. Hopefully you can use this to give the second equation a go. So we have x is equal to 4 minus t squared and y is 2 plus t. We've been given that the gradient is 5 over 6. So how do we find the points? Well, again, we need dy by dx. Dx by dt is minus 2t. Dy by dt is 1. So we're going to get to dy by dx using our formula is 1 dy dt divided by dx dt minus 2t. And the minus, it doesn't matter. We can put that in front of the fraction, at the top of the fraction, or at the bottom. Now we've been given that our gradient is 5 over 6, so let us substitute this in for dy dx. So dy by dx is the gradient, which has been given to us is 5 over 6, and we know the formula for this is 1 minus 1 over 2t. Now how do we solve this? Again, we have fractions. Multiply by the denominator, cross multiplication will give us 5 times 2t will give us 10t. 6 times negative 1 will give us minus 6, which will leave us with t is minus 0.6. Or if you want, minus 6 over 10, which is 3 over 5. So we now have a value for t. We now know what t is. But remember, we want the points. So make sure you substitute t back in. I'll leave this for the exercise to substitute these values back in. And I have given you already the solutions to this question, so you will be able to check your working. So at the bottom is our final answer over here. So implicit differentiation is another part that we need to go through. It is also considered a little bit harder than normal differentiation, but once you've done a few examples, it is not that difficult. You will see in our second example that we're doing here a very common trap that we encounter during exams, which will often lose students marks because they forget to use an important rule. So what is implicit differentiation? Implicit differentiation is when you have an equation where x and y is randomly in any part, left-hand side, right-hand side, or both. And x and y can be combinations as well. So you could have, just like in the last question, x times y in the equation. So this means we don't have a formula where we have y is equal to and then just some formula for x. So if you encounter a question like this, you need to remember how to do implicit differentiation. We simply differentiate on both sides of the equal sign, but we need to always remember the chain rule when we take the derivative of y. Because when we think about it, we want y to be a function of x. So every time we have y, we have a, in brackets kind of, invisible, anything, any formula for y. So we need to then, when we differentiate this, multiply by the derivative of y. Now the derivative of y is always dy by dx. I highly don't recommend to write y prime because the little prime is very easily confused with other y's. So let's do these couple of examples together. The first question is going to give us x to the power of 3, x to the power of 3 plus y is equal to 3. So now we're going to differentiate both sides. So we're going to differentiate this side first, and again we have plus, so we can do them one by one. X to the power of 3 will differentiate to 3x squared. And now y, well, if y is just by itself, then that would differentiate to 1. So plus 1. But we need to be careful. Every time you take a derivative of y, you just have to write down multiply by dy dx. Now, if we differentiate the right-hand side, that is very easy. Differentiating a constant will just give us 0. So what we get is we get an equation where we have dy by dx in it. This is now the derivative that we're looking for, but if we want to, we should rearrange to get this as a formula in terms of x and y. So simplifying this will give us dy by dx, and moving 3x squared to the other side by doing minus 3x squared on both sides will give us a formula for dy dx. And now we note this is only in terms of x. This formula can be in terms of x and y, just like our original function that we had implicitly defined as. Now, let's do the second example. Here we had xy is equal to x squared plus y squared. Okay, now again we can identify we have one formula with x's and y's and combinations. So we need to differentiate implicitly. Well, how do we do it? Differentiate both sides with respect to x. If we differentiate this part, and this is where the trick or the part comes in that you need to recognize, x is a function, y is a function in terms of x. So this is two functions multiplied together. So we need to use our product rule here. And if you remembered the words that I've given you for our product rule in the last video, then we will see that here we will get the second, which is y, times the derivative of the first, which is x, plus the first, which is copying x, times the derivative of the second. Now the derivative of the second is 1, but here we're taking the derivative of a y, so we need to again add dy by dx. Now, in differentiating the right-hand side is very similar. So let's have a look. If we're differentiating x squared, we get 2x. Differentiating y squared, well, that will give us 2y. But again, every time you have a derivative of something with y, you have to multiply by dy by dx. And now we have a very long equation that gives us the derivative in terms of x's and y's. Now, at this point, check what your question wants from you. Do you just want to figure out what the gradient is? Then you can just substitute in x and y values and then simplify and solve for dy by dx. If you were given a question where you actually need to write the equation for the derivative, then you have to simplify this and rearrange for a formula for dy by dx. So let's do that in case you have to do that. First of all, we want everything that has a dy by dx on one side and everything else to the other. So here we have the terms with dy dx, and here we have the terms that do not have dy by dx. Let's move them around. X times dy by dx can stay on this side, and we do minus 2y dy by dx. And now we leave 2x on this side, and we do minus y on the other side. Now, in order to get to our dy's, we need to factor out the dy. We get dy by dx is equal to x minus 2y, and we copy the left-hand side. And now, if we just want dy by dx by itself, we can divide by this whole term. Then we get 2x minus y divided by x minus 2y, and we get our equation as we wanted. Fantastic. Now let's have a look at our next slide. Yeah, we just have some examples. Pause the video now. Make sure that you're familiar with implicit differentiation. Just getting a question right that has implicit differentiation will immediately push your mark up. So give these a try and then make sure you get the right answers. I don't actually provide your answer for this one, so make sure you're getting these right. Go back to how we were doing our questions and writing them down. If you have questions, make sure you put them in the comments, and I will see you next in the third video for topic 3, applications of derivatives.